So now we're going to move on and talk about the natural log function. So we talked about f of x equals ln of x. That's the natural log function. But since that function is a function, so it passes the vertical line test, and since it's 1-to-1, then it must have an inverse. And the inverse of the logarithmic function is the exponential function e to the x. And remember, we talked about this in a previous video, how we can convert back and forth between a logarithmic function and an exponential function. We also reviewed exponents and exponents rules. So if we multiply and we have the same base, we add the exponents. For instance, if we have e squared times e cubed, then that would be e to the 5th. And then if we divide and we have the same base, we subtract exponents. So if we have e to the 5th over e squared, it's going to be e to the 5 minus 2. It's always top exponent minus bottom exponent, which is e cubed. Domain properties of e to the x. E to the x is always going to be positive. It's an exponential function. The range is always going to be from 0 to infinity. We can type any number in for that exponent, but we're only going to get numbers out between 0 to infinity. Notice we are going to not get 0, so we're not including that 0 there. That's why there's a parentheses. E to the x is going to be a continuous function. It's always increasing, and it's always 1-to-1. We could talk about concavity. This guy is going to be concave up. We can talk about horizontal asymptotes. If we were to take the limit as x goes to negative infinity, we're going to get 0. So that tells us this guy has a horizontal asymptote at y equals 0. But if we try to head to infinity, so as x goes to infinity, e to the x is going to increase without bound. So it's going to get bigger and bigger and bigger, so it will head to infinity. If we want to take the derivative of e to the x, the derivative of e to the x is e to the x. And then using the chain rule, if we take the derivative of e to the u, it's going to be e to the u times du. And we could even write that this way, using the notation we've been using all course. So just a quick example to see that. Let's say we want to take the derivative of e to the 2x. The derivative of e to the u is e to the u, so it would be our e to the 2x, but then we have to take the derivative of the exponent, which would be 2. So we would get 2e to the 2x there. So integration is going to be really similar. If we want to integrate e to the x, we will get e to the x. If we want to integrate e to the u du, then we will get e to the u plus c. And remember, with integration, we can always check our answer. If we were to take the derivative of this, we should get back whatever we're trying to integrate. So I want to start with a quick review of solving logarithmic or exponential equations. There's a more extensive review in Blackboard that slows this process down a little bit if you want to take a look at it. Just for a reminder. So let's look at 8. Let's say we want to solve this equation for x. Our first step would be to try to isolate this term. So we can add 12 to both sides. And when we do, and I'm going to write this over here, we're going to have 8x is equal to 19. Sorry, 8e to the x is equal to 19. So we can divide both sides by 8. And then to get this x down, we would take the logarithm of both sides. Now I'm going to use the natural log. So when we take the ln of e to the x, that's one of our properties of logarithms. That's going to give us x. So x is going to be equal to the ln of 19 over 8. 17 is a logarithmic equation. You have to remember the base. So here the base is e. So let's rewrite it as an exponential. The base is e, the exponent would be 1, and that would be equal to the square root of x plus 2. So e to the first is just e. So now we can square both sides. If I take e and I square it, I'll get e squared is equal to x plus 2. And then if we subtract 2 from both sides, we're going to get e squared minus 2 as our x value. So with logarithmic functions, you always want to check the domain. If we were to check the domain here, we would need the square root of x plus 2 to be greater than 0. So x plus 2 has to be greater than 0, so x has to be greater than a negative 2. And this guy, if we were to type that in the calculator, it's definitely bigger than negative 2. So we're going to be okay there for that answer. Remember, changing logarithmic equations to exponential does open the door for extraneous solutions. So you always have to check. So now let's move on to derivatives. Let's say we want to find the derivative of something like this. I'm going to write it over here. So let's think about that u substitution. Let's let u be that exponent, negative 2x cubed. So du would be negative 6x squared. We could do our rewrite. So y equals e to the u. And then when we take the derivative, it's going to be e to the u times du. So if we make our substitution, our derivative will be e to the negative 2x times negative 6x squared. And I would want to write that as negative 6x squared times e to the negative 2x, just to clean it up just a little bit. So we can use that chain rule to help us find derivatives of these. Let's look at 39. So we have two functions here. We have e to the x and we have ln of x. So to find the derivative, it will be a product rule. Product rule says it's the first one times the derivative of the second plus the second times the derivative of the first. So I would want to clean this up just a little bit. I'm going to rewrite this as e to the x over x plus ln of x times e to the x. Now if we wanted that common denominator, we can multiply the second one by x over x. So I'm going to do that. So then we would have e to the x plus x ln of x e to the x all over x. And so we could factor out an e to the x, and that would leave us with 1 plus x ln of x all over x. So any of these would have been acceptable. Lots of different ways to write answers. Let's do another one. Let's look at 75. So if we want to solve and find the derivative for this one, I would want to rewrite this first, distributing that e to the x. Oh, let's not do that. Let's leave it as 2 minus x times e to the x. We could distribute. There's lots of ways to go about this. So here's what I see. I have a function here, and I have a function here. So I'm going to use that product rule again. So the derivative would be the first one times the derivative of the second plus the second one times the derivative of the first. And the derivative of this guy would just be a -1. So this is going to be 2 minus x times e to the x minus e to the x. And notice both of these terms have an e to the x in common. If we were to factor that out, we'll be left with 2 minus x on the first one and a -1 on the second one. Simplify the parentheses. 2 minus 1 is a 1. So there's our final answer for that derivative. We could have distributed that e to the x, and we would have gotten the same answer. So now let's work backwards and talk about integration. So if we wanted to integrate something like this, let's think about our u substitutions. What if we let u be that inside stuff, e to the x plus 1? Then du would be the derivative of that, and the derivative of that would be e to the x times dx. So you can see that e to the x and that dx, both of those components make up du, and this guy's u. So if we do a rewrite, we're going to have u squared times du. We can integrate. That's going to give us u cubed over 3 plus c. And then if we sub back in, we're going to have e to the x plus 1 cubed over 3 plus c. So there's our final answer. So we're going to start combining lots of rules, those exponential rules, those logarithmic rules, and the reverse chain rule, all into one problem. Let's look at 97. So let's think about what u would be. So this is the problem right there. So let's try to let u be that. Let u be the square root of x. So let's find du. Square root of x is the same thing as x to the 1/2. So if we take that derivative, bring the exponent down, subtract 1 from the exponent, and so we took the derivative with respect to x. So we're going to have 1 over 2 square root of x times dx. So you can see where this guy's coming into play. I'm going to rewrite this slightly. So you can see where the pieces are. Anytime we have an exponential with some kind of interesting exponent, try letting that exponent be u and see if that helps the problem out. So in this case, if we do that, we see that this is going to be our u. So we have part of du here, but we're missing that 2 in that denominator. We could rewrite this way, 1/2 times 1 over square root of x dx. So you can see we're missing a 1/2. We can multiply that in as long as we compensate with the 2 somewhere else in the problem. So then now, if we do our rewrite, we have a 2 on the outside. We're integrating e to the u, and that 1/2 times 1 over square root of x dx is all of our du. So if we integrate e to the u is e to the u. Don't forget the plus c. And then if we sub back in, we have 2e to the square root of x plus c. There's our final answer. Let's look at 99. We want to integrate e to the negative x over 1 plus e to the negative x dx. So these are just going to keep getting more and more interesting as we go through this course and then subsequent courses. Let's try this. Let's let u be that denominator, 1 plus e to the negative x. So if we were to take the derivative of that, we would have to take the derivative of this piece. Derivative of 1 is 0. The derivative of e to the negative x is e to the negative x times the derivative of the exponent, which would be negative 1. So that would be negative e to the negative x dx. So you can see how we're missing a negative 1 in front of this guy. We can multiply a negative 1 in as long as we compensate with a negative 1 outside the problem. So now we have all of our du, and then we have u in the denominator. So then when we do our rewrite, we have negative integral. The negative 1, e to the negative x dx, all of that circled in red is du. And then our denominator, all of that is u. So check this out. This is actually the natural log rule. When we integrate that, we're going to get negative ln of u plus c. That absolute value is important. And then when we sub back in, we have negative ln of 1 plus e to the negative x plus c. So because we're dealing with exponentials, 1 plus e to the negative x. So remember, e to the negative x is always going to be a positive number. If I take a positive number and I add 1 to it, I'm still going to get a positive. So that absolute value is actually not necessary in this particular case. So we would have that. I'm going to tweak this just a little bit. Remember that negative is actually the exponent. So we could rewrite it that way. And that is the same thing as 1 over 1 plus e to the negative x plus c. And usually we don't, if we can, we don't want to leave negative exponents in the problem. So let's do a trick here. What if we were to multiply by e to the x? If I do that to the top, I have to do that to the bottom. Math is always fair. So remember, there's an understood parentheses around that term. So then if we rewrite that, we're going to have e to the x in the numerator, and then we're going to have 1 times e to the x, which is e to the x, plus e to the x times e to the negative x is e to the 0 When you multiply and you have the same base, you add the exponents. And e to the 0 is really 1. So that helped us simplify without having to deal with complex fractions. So that's another way to write this answer. So it would have been fun to leave it like this, or to rewrite it like this. And let's look at 106. 106 is integrating e to the negative 3x plus 2e to the 2x plus 3 all over e to the x. So one thing we would want to do is split that numerator. So we can rewrite this as e to the negative 3x over e to the x plus 2e to the 2x over e to the x plus 3 over e to the x. Okay, algebraically, that's equivalent. We have the same denominator, so we would add the numerators. It's always good to double check in this step to make sure you have the same thing you started with. When we simplify, when we divide and we have the same base, we subtract the exponents. So negative 3x minus x is a negative 4x. 2x minus x is a 1x. And then this guy, we're just going to bring that e to the x to the numerator by making that exponent negative. So now we're going to have to integrate each piece separately. Every one of these is going to be a chain rule or reverse chain rule. So let's think about our u substitutions. If u is this negative 4x, du would be negative 4 dx. So we're missing the negative 4 here. We can multiply it in as long as we compensate with a negative 1/4. So if we integrate that piece, when we integrate e to the u, we're going to get e to the u. The next one, we have 2 times this integral. When we integrate e to the x, it's just e to the x. And then this last one, this is reverse chain rule again. There's our u. Du would be a negative 1 dx. We can multiply the negative 1 in as long as we compensate with the negative 1 outside. So we're going to have a negative 3 there. And then when we integrate e to the u, it would be e to the u. And then plus c. So there's our final answer. Once you have done these a few times, chances are you'll probably stop writing out that u substitution every time. If you want to write the u substitution out, like we did over here in 99, definitely do that. And let's do a few more problems. So now we're going to talk about definite integrals. And let's look at 109. So in 109, we want to integrate from 0 to 1 of e to the negative 2x dx. So I want you to start thinking about that u substitution. We're going to let u be that exponent. So if u is the exponent, negative 2x, du would be a negative 2 dx. So we are missing the negative 2. We can multiply it in as long as we compensate with a negative 1/2 out here. So I'm going to do this one without writing out that u substitution. So there's our du. When we integrate, we're going to have negative 1/2. And then integrating e to the u is going to be e to the u. And we're going to evaluate from 0 to 1. So we're going to stay in the world of x for this particular problem. So we're going to have negative 1/2. And we're going to substitute that 1 in. If we substitute 1 in, we're going to have a negative e to the negative 2 minus. If we substitute 0 in, it's going to be e to the 0. So negative 1/2. This is e to the negative 2 minus 1. I'm going to clean this up just a little bit. E to the negative 2 is 1 over e squared minus 1. If we get that common denominator, we would multiply by e squared over e squared. So we have 1 minus e squared all over e squared times the negative 1/2. So there's our final answer. Let's look at 111. I'm going to reorder this. This is e to the negative 2x times x dx. E to the negative x squared. Oop. So thinking about that u substitution again, we could let u be this. So what would du be? If we take the derivative of negative x squared, we're going to have a negative 2x dx. So we need the negative 2 here. That will give us negative 2x dx as du. But if we multiply by a negative 2, we have to compensate with a negative 1/2. So then when we integrate, we're going to have e to the u. And then we're going to use that fundamental theorem of calculus. If we plug that 1 in, we're going to have e to the negative 1 minus e to the 0. E to the negative 1, I'm going to write that as 1 over e. E to the 0 is 1. That common denominator would be e. So we're going to have 1 minus e over e multiplied by negative 1/2. There's our final answer. Now, if you want to write the u substitution out, feel free to write the u substitution out. Just for fun, let's go through and do the u substitution on this one. I don't know what's going on with my tablet. So we're integrating from 0 to 1, e to the negative x squared x dx. We would start, this is still 111 by the way, we would start by letting u be that exponent, negative x squared. So du would be negative 2x dx. So this is where we would say we're missing that negative 2. We can multiply it in as long as we compensate with a negative 1/2. So then when we do our rewrite, we would have negative 1/2 times the integral of e to the u times du. That negative 2x gets absorbed into that du. But this is where we have to figure out bounds. So let's do that over here. Let's start with that lower bound. If x is equal to 0, because that's what we said over here in the original integral, then u would be negative x squared, which is negative 0 squared, which is still 0. So that lower bound will stay at 0. Let's check out what the upper bound does. So in the original, that upper bound was 1. But when we substitute that into our negative x squared, then we're going to get a negative 1 out. So notice that top bound is smaller than the lower bound. I would want to flip that. And if we flip that from negative 1 to 0, remember that changes the sign. So instead of a negative 1/2, it's going to become a positive 1/2. That was one of the properties of integrals back in chapter 4. So now when we integrate e to the u, we get e to the u. And we're going to evaluate from negative 1 to 1. Sorry, negative 1 to 0. So we're going to have 1/2. This is going to be e to the 0 minus e to the negative 1. So this is 1/2 1 minus 1 over e. And if we get that common denominator, this would be 1/2 times e minus 1 over e. Okay, which is the same thing that we got over here. If we were to distribute that negative in here, it would be a positive 1/2 negative 1 plus e over e. So you can see how we get the same thing either way we do it. So we can switch to the world of u like we did over here, or we can stay in the world of x like we did over here. Either way is fine. Let's look at that last problem, 116. We are integrating from negative 2 to 0, e to the x plus 1 over 7 minus e to the x plus 1 dx. So this is when you may want to write that u substitution out. Here's what we're going to do. Let's let u be that denominator. So du would be the derivative of this. Derivative of 7 is 0. The derivative of negative e to the x plus 1 requires chain rule. It's going to be negative e to that exponent times the derivative of the exponent. So our du is negative e to the x plus 1. So anytime we have exponents in the top and bottom of a fraction, the best way to start is to think about letting that denominator be equal to your u, and then see if the numerator is your du. So in this case it is. So I'm going to rewrite this so we can make this a little bit easier to see. This is 1 over 7 minus e to the x plus 1 times e to the x plus 1 dx. So you can see the only thing we're missing from du is that negative 1. We can multiply by a negative 1 as long as we compensate with a negative 1 out here. So then when we do our rewrite, we have negative All of this is du. That denominator is u. So it's 1 over u times du. We just have to figure out bounds. So let's look at the lower bound. So if x is equal to -2, then u would be e to the -2 plus 1. Just kidding. U would be 7 minus e to the -2 plus 1. Ooh, guys, this one's going to be really messy. So this is 7 minus e to the -1. Remember, to find this, that has to go in for that u. Let's look at our upper bound. So if x is equal to 0, that was the original, then u is equal to 7 minus e to the 0 plus 1, which is 7 minus e to the first, or 7 minus e. So lower bound is 7 minus e to the -1. Upper bound is 7 minus e. This is 1 over u times du. So when we integrate this is your ln rule. We're going from 7 minus e to the -1 to 7 minus e. So when we integrate, this would be the ln of 7 minus e minus the ln of 7 minus e to the -1. Now, keep in mind, 7 minus e would be a positive number. 7 minus e to the -1 would be positive. So the absolute value is not necessary here. So I'm going to rewrite this. I'm going to distribute that negative in there. And then I'm going to reorder. So this is the ln of 7 minus e to the -1 minus the ln of 7 minus e. We can actually combine those using logarithm properties. But before we use the logarithm properties, let's simplify this. So this is 7 minus 1 over e. And that's going to be 70 minus 1 over e. Just finding that common denominator there. Minus the ln of 7 minus e. So ln of 7e minus 1 over e. And then we're going to divide that by the 7 minus e to combine these logs. Subtracting, we would divide those arguments. Divide, you keep, change, flip. So this is going to become ln of 7e minus 1 over e times 7 minus e. So there's various ways we could write this. We could stop right up here. That would be perfectly fine. This is not a very nice number, but it is a number. We can use logarithm properties. We could stop here. We could expand this out and simplify this just a hair more if we wanted to. So there's lots of ways we could think about solving these. I'm going to leave it in that form. That way it's all condensed into one log.